this, when you get into the nuts and bolts of it, gives us Kepler's laws. You guys know Kepler's laws? No? All right, I need a volunteer to run up to the math department and grab the gallon of milk that I put in the refrigerator. Mr. Anderson, I choose you. It's in a Walmart bag. It's in the, you'll find it.
All right.
It's not opened yet. All right. All right, so I should, let's see here. Let's give you an example to work on. While I'm setting up our party. Let's see here. This is the Isaac Came to Class party, if you're wondering why. So the questions you guys are starting to ask about geometry and things, we are going to get back to. We're going to talk about the so-called Frenet frame to a curve, which is the tangent normal by normal. We'll talk about that. The first thing we got to talk about, like tomorrow, is arc length. So I think I was supposed to get that today, but I guess we're going to have a party instead. So I think you'll forgive me. And I guess I need to write you more homework, huh? So let me give you guys something to chew on here before you have something to chew on. Example 6. Let's just do something simple. Let's calculate for r of t equal to t squared t cubed with mass m equals to 1. All right, find net force and torque on this particle. So this is the position of a particle. If I give you the mass, you'll be able to find the net force on the particle as well as the net torque on the particle with respect to the origin. Let me restate this problem for you. Calculate the derivative, calculate the second derivative, take the cross product of the second derivative with the function itself. See what you get.
You write down the equation for it.
It's R cross F. So what are you doing?
Building my plane.
You Minecrafting?
Mm-hmm.
All right.
Not finished this plane.
I had the donut holes. I think what we'll do is we'll have you guys the fastest way to do this is take one, pass it on, right? It's really simple for me. I can do the first row.
Well, given they didn't give us any units for anything, if we had units, then it wouldn't quite be the same because force would be in
You can work in whatever units you'd like.
probably.
Use your imagination. You can work in meters, you can work in feet, you can work in astronomical units, you can work in seconds, minutes, fortnights, I don't care. This is one of the great joys of me not teaching physics at the moment. I don't care about units. Not even a little. So feel free to take one. We will have milk here. Who likes donut holes?
Doesn't.
Let's start that way. Who was that?
Thank you.
Okay. Here, we'll start this one back here. I think Michael got lost. Have to go find him. Maybe. Wait a minute. Does Michael know where the math department is? I may have made a mistake here.
You just drank your whole gallon of milk.
What's that? Oh, you can leave it on. It's fine. Eventually, I'll get to this here. You can just leave it here. Yeah, it's cool. Sorry, this feels wrong without milk. Come on, Michael. Oh, here he comes. I see him. He was waiting for the elevator. Ah. That's what it was. Using the elevator. That was the fatal mistake. Now I think I've got an idea about some people. There should be enough for everybody to take like 2 donut holes, I think, or one of the donuts. I'm not sure, actually.
She got kind of scared when I asked her that again.
Who's that? Miss Guthrie?
She was like, I think you're the first person to ever ask that in that department.
It's like, do we have gallons of milk? No. All right. All right, Isaac. I want you to deliver these milks.
We did an amazing thing in Minecraft.
Take these milk to the students, 2 at a time. Just 2. 2 at a time. For you, and for you. Nope, he already got one. Next row, Isaac.
Thank you. Thank you.
Actually, hand these down. Hand it down, actually. That'd be. Don't like milk. How dare you? No, just kidding.
I've never had milk with a donut.
Never had milk with a donut. Oh.
You mean like dunking it?
Thank you.
I'll pass it. I'll pass it down.
Oh, it's okay. Isaac's coming. You can get in here. This row is.
You've already started the milk bucket.
Here you go. Jump in here. Oh, you don't have anything? Okay. Uh-oh. Nah. Who doesn't have milk that needs it?
Multiply by 1.
All right, take it to the fellow on the camera. The cameraman. Who else needs milk? Anybody? Okay. Yeah, you keep playing your. I thought you were gonna do a dizzy dance or something.
Oh, yeah,
You do it in the front, okay?
right.
You should do it like right there,
Here.
right in front of the board. You can do it right here when it's time. It's not quite time yet, Isaac. Not quite time.
What is the special occasion?
Oh, Isaac came to class.
Really?
There, you can go do your dance now if you want. All right, Isaac, go for it, man. Isaac, you gonna do it?
Cameras on here?
That's right.
Oh, you can see when Isaac walks by his little head.
Yeah.
Top of it.
Yeah. I don't know. He's got something prepared. Do your thing, Isaac. Now you can just go up there and do it so they can see it.
They didn't do anything.
Are you making them dizzy? I don't think it worked. You should try it some more. Maybe you should try it some more, huh?
I just stopped doing it.
You gonna stop doing it? Oh, okay, that's fine. Wow, did we finish the donuts?
Donut guy.
What's that? Can you have a donut? I'm afraid not, Isaac.
Thanks again.
We'll go get some from somewhere, Isaac. Okay, don't worry. You done with that milk? Oh, so yeah, let me tell you the answer and we'll be done, right? So dRdt is 1, 2t, 3t squared. Acceleration, 0 to 6t. You got it zoomed back. You got it back? Is it zoomed?
This is a pretty tough class.
It's the top thing, yeah. You can go side, left and right. See it? All right, ahem. Just a sec, guys. So the force is oh, that reminds me. So like, I'm in like a very serious junior level class on classical mechanics, right? And we're talking about Newton's laws, right? And the professor goes, but so, where's the force? And this guy whips his hand up. He's like, Professor, the force is everywhere. like we laughed for like 2 minutes, professor included. It's just excellently delivered. So the force is a function of, to achieve this motion, you need a force which is a function of time. In particular, you need a variable force, time-dependent force to produce that motion, which is all twisty. And the torque is what? Torque is equal to R cross F, which would be t squared, t cubed, crossed with this 0 to 6t. What do we get? 6t cubed minus 2t cubed.
0 minus 6t squared.
Minus 6t squared.
Yeah.
2t. So in other words, we could get, you got 4t cubed minus 6t squared, 2t. So this force definitely is not a central force, right?
Yeah.
The torque is far from 0, and then the motion's all twisty. Like this is I think it's a twisted cubic. It looks something like, if you graph this thing, I don't know, it's just all twisty. Yep.
So, random question. If you took the derivative of that,
The derivative of torque,
maybe the change in the...
I don't know. I can tell you that if you differentiate acceleration, it's the jerk. But that's about all I know. So anyway, see you guys. We're done.